Okay, so in this video, we will quickly review the chain rule of differentiation. So if you remember, the chain rule is applied when you have a composition of functions, and the key word for a composition is of. So if you differentiate f of g of x, you have a composition. And the chain rule works a little bit like if you were peeling off an onion. You start from the outer layer, and you keep peeling off the following outer layer until there's nothing left over. The outer layer is the outer function, and peeling off is the action of differentiating. So here f is the outside function, so we differentiate f. We get f prime of what? Of the argument. F prime of g of x. But there's still g of x left over. The chain rule says you have to multiply whatever you have so far by the derivative of the leftover function. G of x is left over. We differentiate, we get g prime of x, and now there's nothing left over, and that's the result of differentiating f of g of x from the chain rule. F prime of g of x, peeling of the first layer, times g prime of x, peeling of the second and final layer. We could easily differentiate over a composition of three functions, so f of g of h of x. Again, the outer function is f. We're peeling it off. We're differentiating. F prime of what? Of the argument. G of h of x. Times the derivative of what's left over. Outer function is g. Differentiate g. We get g prime of the argument. H of x. But there's still h of x left over, so times the derivative of what's left over, the derivative of h of x is h prime of x. And of course we could repeat this over a composition of 4, 5, 6, any number of functions, and it works the same way. You differentiate the outside function, evaluate at the leftover argument, and if there's anything left over, you have to multiply what you have so far by the derivative of the leftover function. So let's consider a few examples now. What if we differentiate with respect to x, say sine of x squared plus 3 to the 8th. And if ever you are in doubt as to what is, because sometimes it can be a bit confusing as to which is the outer function, always imagine yourself trying to evaluate for a given value of x the expression, and the last thing you would compute is the outer function. So here, if you thought of taking, let's say, x equals 2, then you'd first square to get 4, you'd add 3 to get 7, then you'd take the 8th power, and then once you have this value, you take the sine of the value. The sine is the outer function. By the chain rule, we differentiate the outer function, the derivative of sine being cosine. Of what? Of the argument. X squared plus 3 to the 8th. But we're not done. So times the derivative of what's left over. Here, the outer function is the power 8 function. So we use the power rule. We bring the exponent down. We subtract 1 from the exponent. What is the argument? What's left over? X squared plus 3. Are we done? No. There's still x squared plus 3. We have to multiply what we have so far by the derivative of the leftover function, x squared plus 3. The derivative is clearly 2x from the power rule. And that's it. What about this example now? The derivative with respect to z of, say, cosine squared of 1 plus e to the z cubed. And here you have to ask yourself, which is the outer function? Is it the square function or the cosine? The answer is, it is the square function. When you put the exponent on the trig function, what you mean is evaluate the trig function of the argument and then square the whole thing. So here the outside function is the exponent. We differentiate, we get to use the power rule on the exponent of 2, bring 2 down. Subtract 1 from 2, you get 1 of what? Of what's left over, cosine of 1 plus e to the z cubed. But we're not done, there's still cosine of all this left over. We multiply by the derivative of cosine, which is negative sine. Negative sine of what? Of what's left over. Are we done? No, there's still this left over. Again, we reapply the chain rule, we multiply what we have so far by the derivative of what's left over. Derivative of 1 is 0, plus the derivative of now e to the z cubed. Now here, which is the outside function? Is it the cube, z cubed, or is it the exponential? Well, again, imagine yourself trying to evaluate this expression. Suppose you pick z equals 2. If you want to evaluate this, you'll first have to cube 2. So you have 2 cubed is 8, and then you can exponentiate e to the 8th power. The last thing you do, therefore, is the exponential. So we differentiate the natural exponential, which of course gives us the same function, done, times the derivative of z cubed, which is of course 3z squared. Now there's nothing left over, and this is the end result. Let's look at one last example. Let us now differentiate with respect to t. Say the cube root of sine of 2t cosine of 4t. Well, here clearly the outer function is the cube root function, and we think of the cube root, of course, as a power of 1/3, so we can simply differentiate applying the power rule. So the power rule says we bring the exponent down, so we get 1/3, and we subtract 1 from the exponent. So 1/3 minus 1, negative 2/3. The derivative of the exponent, gone. What's the argument? Whatever's left over, sine of 2t cos of 4t. Times the derivative of what's left over. What's interesting here is we must use the product rule, as what's left over is sine of 2t times cos of 4t. Here's the first function. Here's the second function, and make sure to open your brackets because the derivative of this function must multiply all of this expression. So we start, the derivative of sine is cosine. Cosine of what? 2t. But be careful that this is just the derivative of the sine part. There's still the 2t left over, but the chain rule, we must multiply cos of 2t by the derivative of 2t, which is 2. That's the derivative of the first function times the second, cos of 4t. Product rule plus, now the first function, sine of 2t, times the derivative of the second function. The derivative of cosine is negative sine. But we're not done. That's just the derivative of the cosine part. There is still the 4t times the derivative of 4t, which is, of course, 4. And now we complete our product rule. Now we close our brackets. You see, without the brackets, this would be wrong, as it would be this part times only this one. But it really is this times all of this. So always make sure that whenever you apply the chain rule, that you open your brackets. Otherwise, the answer would be wrong. And that's it. So always remember that when you apply the chain rule, all it really is like peeling an onion. Differentiate the outer function, evaluate at the leftover argument. If there's anything left over, multiply what you have at this point by the derivative of the leftover function. And you keep repeating until there's nothing that you have not differentiated.